welcome back. In the last lecture, we introduced a very important quantitative way of finding out the feasibility of a certain process, and that is the inequality of Clausius or Clausius inequality expression. Okay. So now in this particular lecture, we are going to make use of that defined a term called entropy, and as well as we will specifically consider few particular processes. Okay. So let me just first start with specific reversible processes. Here, this is an illustration on a PV diagram. You have state 1 and 2, and here you have two different ways to have a cycle. So let's consider a reversible cycle A and B. So you have A, okay, and B, and in this reversible cycle, this reversibility would be either totally reversible, which essentially means your system and surrounding, and the internal reversible means just a system. That means it's undergoing a quasi-static process or doesn't have any finite temperature based heat transfer. So for the case of AB reversible, we can come up with the expression considering AB is a reversible, and we know that reversible cycle, the Clausius expression is equal to 0. Okay, so that means the equality is there for this del Q by del T is equal to 0, which can be simply the sum of these two paths, A followed by B. Okay, for this, so 1 to 2 for the A plus 2 to 1 for the B. Now we can consider another cycle which will be your B and C. Okay, so this is for another cycle, and the same expression can be written in this following form. So again, it being a reversible cycle BC, this expression is 0, which essentially can be separated by these two paths B and C. Now you can subtract this from this, okay, B being common, which essentially means that you can write the following, where the 1 to 2 from path B should be same as for the case of C, or in other word, this integral based on path A should be same as that of integral based on path C, which means that basically this particular expression is independent of path, and thus this expression just depends on the final endpoint, and this is what we call it as entropy. Okay, because it is independent of path for all reversible paths from 1 to 2. So we write this expression in terms of del S. So this becomes your del S is nothing but del Q by T. We consider only at this point is internal reversible, but this is, as I said, could be for overall total or internal reversible. So considering only the system here, we are looking at only the internal reversible here, and thus your del S is equal to simply your del Q by T. If you can integrate this by having a relation between Q and T, you can come up with this del S, the change in entropy between state 2 and 1. Okay. Now this particular expression, once you calculate, okay, this will be fixed because this expression tells you only the difference between the 2 points 1 and 2. It doesn't depend on how this particular transformation from state 1 to 2 was achieved, whether through your reversible or irreversible process. This is true for irreversible and irreversible processes as well, this particular expression. However, in order to evaluate based on this integral, you need to have a reversibility or internal reversibility. Then you can make use of this expression. So now let's specifically consider an isothermal process. Okay, now for an isothermal process, consider this as a system, and such that the heat is being supplied and the temperature is kept. Now this delta S, as I mentioned, is already, as I mentioned earlier, can be written as 1 by 2 del Q by T internal. Now considering the temperature is constant, you can take out the temperature outside, and this becomes simply the integral of 1 to 2 del Q. Okay, and this essentially is nothing but your Q, which is supplied to the system, considering is a internal reversible. Okay, which essentially means that difference between the surrounding and this should not have a very finite temperature difference. Okay, so based on this, you can calculate the entropy change. Now for the given example, the Q is known, temperature is known, so it's nothing but 750 divided by 300, which essentially is 2.5 kilojoules per Kelvin. Okay. Now let us consider a cycle which is composed of a reversible and irreversible process. So here you have state 1 and 2. The dotted line indicates the process which can be reversible or reversible. Essentially we are not aware of it, but from 2 to 1, the process is internally reversible. Okay, and what we are interested in this Clausius inequality, we write this expression. So for this process to occur, the process should satisfy this condition, that is Clausius inequality must hold. Now we can write this expression by including the contribution from 2-1 process and 1-2 process. Note that Clausius inequality is meant for the cyclic process, okay? But here we are taking contribution from individual process, which is here 1-2 process, and this is 2-1 process. Now 1-2 process is either irreversible or irreversible, which we are not aware of, and this 2-1 process is internal reversible. Thus we can write this in terms of simply the change in entropy, okay? And then this is less than or equal to 0. Now you can take it here, you can write this expression in terms of this, okay? So that means your change in entropy between these two must be greater than or equal to the integral of 1 to 2 del q by t, okay? And this can be written as in a differential form, which we have already mentioned. Or in other words, I can write this as that for a given change in entropy of the system S2 minus S1, that is your delta S system, is the entropy due to the heat transfer, or the entropy transfer due to the heat, that is the gain due to the heat transfer, plus the generation of the entropy within the system due to irreversible process or due to the presence of irreversibility. Thus this is a positive value, okay? This will be 0 only when you have a reversible process. Then you can simply write del S by is equal to 1 by 2 del q by t, okay? So if you consider an isolated system during a process, which essentially means there is no heat transfer, then this term is going to be 0, and your delta S system will be just simply S generation, okay? Considering S generation is greater than or equal to 0, your entropy change for an isolated system during a process will be always increasing or remain constant for a reversible process. So in other words, delta S isolated system will be always greater than or equal to 0. 0 will be the case where for a reversible process, okay? That means if you have a reversible process, the entropy of an isolated system will never decrease. Or in other words, for normal process, there is always an increase of entropy, and this is what we call as increase of entropy principle, okay? So let me just get back to the fundamentals of entropy here. Now entropy is an extensive property, okay, which essentially means that the total entropy of the system is equal to the sum of the entropies of the part of the system. So we can consider an isolated system which is made of many subsystems, and thus your change in the entropy of this particular isolated system is nothing but sum of the changes in the subsystem as we represented here, okay? Now which essentially means this analogy can be taken to system plus surrounding conditions, where you can isolate this system plus surrounding, which essentially means that there is no change in mass, Q, or heat and work transfer, though there will be exchange of the mass, heat and work between the surrounding and system, but overall when we consider surrounding and system, we can consider that to be an isolated system boundary. In that case, the change in the entropy of this isolated system would be just a sum of your system change plus the surrounding change, and that must be greater than 0, okay? Considering isolated system, your delta system plus surrounding should be S generation, okay? Thus S generation is nothing but delta sys plus delta surrounding, okay? So this tells you that universe can be considered as an isolated system, and thus S generation of the universe, which is an isolated system, should be greater than or equal to 0, which means the entropy of the universe keeps increasing all the time. Now S generation should be 0, as we already mentioned, for a reversible process, and for irreversible process should be greater than 0, which essentially means it can never be less than 0, which is an impossible process, okay? So the question is, can the entropy of a system during a process decrease? As we already mentioned, that for entropy of an isolated system should keep increasing all the time or should remain constant for a reversible process. But what about the system here? Now system can have heat and work interaction, okay, as well as the mass flow from the surrounding or to the surrounding. So in other words, your entropy change for a system can be negative. This is an example. For example, if you consider this is an isolated system plus surrounding, the system loses heat to the surrounding, okay, and thus your system entropy decreases because your heat contribution to the change in the entropy is negative, and thus your delta S system is negative. However, the surrounding increases. The overall S generation is positive, which is what the condition is. So the entropy change of system can be negative, but the entropy generation cannot be, okay, of the overall system and surrounding, okay. Let me just touch upon the key points here about the entropy. what we know is the process should occur in a direction where the S generation is greater than or equal to 0. Okay. For the reversible process, it should be 0, but otherwise the process should always increase, produce or create entropy. Now the other important aspect is that entropy is a non-conserved property. Okay. There is nothing called conservation of entropy principle. Only for the reversible case the entropy will remain constant. Okay. But otherwise for actual processes entropy will keep increasing. Okay, the other aspect is considering that S generation is synonymous for irreversibility, which essentially means the higher the irreversibility, higher the S generation is. So the performance of a device can be analyzed by looking at just S generation or the amount of entropy being generated. Okay, so the higher the entropy being generated, which means the performance is decreasing, okay, of the particular device. So this analysis can be used to establish criteria for the performance of engineering devices. Okay, that is based on entropy generation. Based on our discussion, what is evident is that entropy is a property. Okay, and our interest is to find out the change in the entropy. The change in the entropy can be calculated from the measurable properties. However, it is very cumbersome, and thus it's easy to derive the values from with certain reference and put it in the table, as is done for steam and refrigerator fluids. Okay, so typical TS diagram, temperature versus entropy diagram for your pure substance appears in a similar form as for the case of your PV diagram or TV diagram. Okay, so this is your just a schematic diagram for your pure substance, and in a similar we have seen for your TV diagram or PV diagram, you have the left region which is a compressed liquid. The regions between the saturated liquid vapor dome is your saturated liquid mixture, and this is your superheated vapor. Okay. Now for the compressed liquid, we will be making an assumption that the entropy is just approximated with the saturated liquid at the specific temperature. Okay, for your P1 and T1. Again, remember that liquid properties are more dependent on the temperature than the pressure, and thus we are going to make use of SF at T1. Okay, for the case of S1. Now for the saturated liquid vapor mixtures, we are going to just simply use similar expression as done for your VO and H. Okay, and for superheated vapor, this will be the region which will have again based on the table. So the table contains, just like your table A4 and A5 which we have used earlier, has the data for the entropy, but these entropy calculations are with certain reference such as your triple point for water. Okay, and the other aspect, if you look at your T and S diagram, as we know, this entropy of the vapor is going to be higher, because note that the change in the entropy has a contribution to the heat transfer del Q by T, and thus your certain contribution comes from the heat transfer. Now this is a typical your isobars. Okay, that is here, and iso cores are not constant within the dome saturated liquid vapor region, and it has a higher slope compared to that of isobars. Okay, so this is a typical diagram for T and S. Okay, so for the case of entropy change for a closed system and a specified mass, the change can be given as in this form. Okay, so we will be making use of the tables having this entropy values for the case of your steam and the refrigerator fluids, and based on this diagram we can easily calculate in the same way as we have done for TV and your PV diagrams, and this becomes very useful property diagram for calculation of processes where the enthalpy plays a big role, and we will be making use of such diagram in our calculations shortly. Okay, so let's take a specific process. In this process you have, we call it isentropic process. So let's just look at what does the change in the entropy for a fixed mass constitutes of. So the entropy of a fixed mass can be changed by heat transfer, okay, and reversibility. Okay, as we already mentioned, delta S is del Q by T plus S generation. Okay, so this is for a process. So if you want to change the entropy of your system, you can do that by heat transfer or for any other reversibility. So S generation is due to reversibility, and this is your heat transfer. Okay, for the entropy, if you consider to be internally reversible, which essentially means this S generation is 0, and if you consider your adiabatic, then delta S should be 0. S should be constant or delta S should be 0. So this would be the case for internally reversible and adiabatic process. Okay, and if you plot your TS diagram, this would be a vertical line. okay, because at a specific constant. So this example of isentropic process where the entropy is constant could be given in the form of adiabatic turbine, okay, where essentially you have no irreversibility, internally reversible, and no heat transfer, okay, and then your S is going to be constant in such a process, okay. So this is an example of adiabatic turbine where the entropy is constant. Okay, so as I mentioned, the property diagram becomes extremely useful to explain processes, and similar to your PV diagram or TV diagram where we looked into the processes related to first law of thermodynamics. For the case of processes where you have to apply your second law of thermodynamics, the TS diagram or your HS diagram becomes quite useful diagrams for explaining or analyzing the process. So this is an illustration of your TS diagram, where this curve is of course the internally reversible process, and this area here would be nothing but your TdS, okay. So this TdS would be your delta Q, considering your ds is for the internally reversible is nothing but delta Q by T, okay. You can analyze your differential heat supplied or heat transfer to the system. So on a TS diagram, the area under the process curve represents the heat transfer internal reversible processes. So this is what I mentioned here, del Q internal reversible is TdS, or Q internal reversible would be simply the integral of this. You can write this expression in terms of your per unit mass, okay. So for the internally reversible isothermal process, this T is going to be constant, T will become your T0, and if you integrate it, this becomes simply delta S. For the unit mass basis, this can be written as simply T0 delta small s, okay. So enthalpy entropy diagram is quite valuable in the analysis of steady flow devices such as turbine, compressor and nozzle, okay. So for the case of adiabatic steady flow devices, the change in the enthalpy is a measure of a work output, for example for turbine, and the change in the entropy is a measure of your irreversibility associated with the process. So thus your property diagrams such as your TS and HS becomes a great visual aids in the thermodynamic analysis of the processes where the second law analysis have to be done, okay. So let me just conclude this particular lecture with this example. This is an example of isentropic expansion of steam in a turbine. Here the steam enters in an adiabatic turbine at 5 megapascal, temperature is given here 450, it leaves at 1.4 megapascal. Now considering is adiabatic turbine, okay, so this entropy is constant. What we need to do is determine the workflow. This is your diagram, TS diagram. So this is the isobars, 1.4 megapascal, 5 megapascal is here. These are all as superheated vapor. One is here, and considering is a constant entropy, there is a vertical and drop here, and this is your process path. So we need to find out the work output. So one can start assuming first with a steady flow device. It's a reversible, which essentially means that your mass, your entropy, energy of this particular system or control volume here is going to be constant. The energy balance can be written in this form, E in minus E out, and considering this a steady flow process, this is going to be 0, okay. So thus you can write your E in. E in is nothing but your contribution due to your mass flow. So MH1, considering your KE and PE remains 0 or the changes are 0 in KE and PE, and E out is your W out plus the contribution due to mass flow out of the control volume. So this is going to be W out plus MS2. So you can write this W out in simply mass rate multiplied by the change in the enthalpy, okay. So what you need to find out is simply this enthalpy of state 1 and state 2, okay. Now the state 1, you can take out the table of superheated vapor. It's given here H1 and S1. Now considering that for the case of state 2, you have the information of 1.4 megapascal and the entropy. Again you make use of the table and find out where this condition meets. That means P2 is this and S1 is this, and you may have to do some interpolation to obtain the value S2, okay. So this is a generic process to solve such a problem based on the information of entropy, which basically in this case we have considered entropy to be constant, okay. So W out for this problem turned out to be your 349.8 kilojoules per kg. So that will be the end of this particular lecture. So I hope it is clear the definition of entropy, making use of Clausius inequality, the process diagram for related to the entropy or particularly second law of thermodynamics, and how to make use of it in order to solve certain problem. Okay. In the next lecture, we are going to explain this entropy change for ideal gas, and we look into some other examples. Okay. So see you in the next lecture.